Greetings. This is back to Chapter 11, Infinite Sequences and Series. This is a continuation of Section 11.9, which is dealing with representations of equations by power series. So I'm going to go over an example here. Evaluate the indefinite integral as a power series. What is its radius of convergence? So we're looking at the integral of x squared times the ln of 1 plus x dx. And so what we first want to do is express that function as a power series and then integrate it term by term. And don't forget to add the arbitrary constant plus c. So we first start off with the known series ln of 1 plus x, and that equals the sum from 1 to infinity of minus 1 to the n minus 1 times x to the n over n, right? And we derived that last time. Next, we would multiply by x squared. And so we're going to multiply that sum by x squared. And given that the operator infinite sum from n equal 1 to infinity, n is the variable, we do want to just distribute this x squared in here and use our exponent rules and deduce that our function has a power series representation of x to the, or minus 1 to the n minus 1 over x to the n plus 2 over n. So now, when we go to integrate with respect to x on both sides, that operator has variable x, and n is a constant. So we see here that that summation, the constant values are minus 1 to the n minus 1 over n, and I'm just integrating x to the n plus 2. And that is quite simple to do. And we get c plus, and we usually want to put the c before our summation sign so that we see it instead of in the end. And now our integral here is x to the n plus 2 plus 1, which is n plus 3. And then, of course, we divide by that exponent. And that is our integral as a power series. Now, because ln of 1 plus x has radius of convergence r equal to 1, our integral x squared has x squared ln of 1 plus x, and the integral of x squared ln of 1 plus x dx have the same radius of convergence. Which is r equal to 1. Good. So we can do another one where we can calculate a definite integral as long as our limits of integration fall within the radius of convergence around the center of that power series. So this is an application of power series. If we notice that in this example, x squared ln of 1 plus x dx, you can use integration by parts a couple times, or maybe once, to calculate that integral. But you can also, if you did not see that, you can use the estimation technique of calculating the integral using a power series. So let's cross this off and let's go and take a look at another example. So how about use a power series to approximate the definite integral. accurate to 6 decimal places. And let's use the integral of 0 to 1/2 of arctan of x over 2 dx. And just to be clear, on known series, arctan is equivalent to inverse tangent of x over 2 dx. So let's begin with that. And we did derive last time that we begin with inverse tangent of x as a known series is equal to the summation from n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1. And so now if I want to calculate the series of inverse tangent of x over 2, I'm going to, wherever x appears, I'm going to substitute x over 2. And now I'm going to re-express that in terms of a proper power series form. So this is going to equal n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2 to the 2n plus 1 times 2n plus 1. Good. So far so good. Hope so. And now we are going to take our integral, right? So if this is inverse tangent of x over 2, and now I am going to calculate the integral with respect to x, I will be taking the integral with respect to x again. So looking at that expression inside my power series, negative 1 to the n is a constant for that integral. 2 to the 2n plus 1 is a constant for that integral, and 2n plus 1 is a constant for that integral. So we're just integrating with respect to x, and so we're just going to take that integral. And we end up with the sum from n equals 0 to infinity of minus 1 to the n over 2 to the 2n plus 1 times 2n plus 1, and now I'm going to take that integral, and taking that integral I get x to the 2n plus 1, which is plus 2, and I want to divide by that value. Now I need to calculate my definite integral from 0 to 1/2. So here I go using the fundamental theorem of calculus, and wherever I have x, I'm going to do my big f of 1/2, take away my f of 0, and my f of 1/2, I'm going to substitute where x appears, I'm going to substitute that 1/2. So I end up with the integral of, or summation, n equals 0 to infinity of minus 1 to the n times 1/2 to the 2n plus 2 over 2 to the 2n plus 1 times 2n plus 1 times 2n plus 2. Take away, and then we actually have, since x is going to be 0 here, we're going to end up with just a, this one, it's going to equal 0. So now we can just simplify this and start calculating terms, and it does ask, what can you calculate the definite integral accurate to 6 decimal places? And I want to point out that we are looking at an alternating series. And remember, with an alternating series, for that, your absolute value of r sub n is going to be less than or equal to b sub n plus 1, the very next term. So in just calculating the first couple terms here, I do see that for n equal to 0, we will have minus 1 to the 0, so, and then 1/2 to the, well, it might be worth it to actually write out what the summation is to simplify. N equals 0 to infinity of minus 1 to the n over 2. We have from here to here, we've got 2 to the 2n plus 1 times 2 to the 2n plus 2. So that's going to be 2 to the 4, right? Or to the 4n plus 3. Good. Over 2n plus 1 times 2n plus 2. And so my very first terms are going to be, for n equal to 0, I'm going to get 1 over 2 cubed times 1 times 2. And then I'm going to have a minus 1 over, and this is for n equal to 1. I have 2 to the 7th times 3 times 4. I'm going to get plus 1 over 2 to the 11th times 5 times 6. I'm going to get minus 1 over 2 to the 15th times 7 times 8. And I'm going to get plus 1 over 2 to the 19th times 9 times 10 minus ... And I see here that this value could be my b sub n plus 1, because that looks like it's going to be less than 6 decimal places. That's going to be less than or equal to 10 to the minus 7. And so I do want to have 6 decimal places, just add 1 to that exponent, and you can make sure that you're going to have a small enough remainder that will not impact your sum. So adding these numbers up together, I get that my estimate is going to be 1 over 16 minus 1 over 1536 plus 1 over 61,440 minus 1 over 1,835,108, and that is going to be roughly 0.061865, and that's going to be my estimate. Good. So notice here that I can use my integral, right? I can use my known series to find a power series for another function. I can use derivatives and integrals for that function and integrate term by term from my power series. And here I'm using the fundamental theorem of calculus, and my range of my limits of integration fall within the interval of convergence for my function, so I can use it as, I can use the power series as a nice substitute for my integral and integrate term by term. And I notice here I'm using the application of alternating series, and so I really can come up with an estimate for my alternating series and calculate an estimate to within 6 decimal places. That does it for this demonstration. I hope that this is a nice introduction to applications of power series, and I will continue with another section on